No matter what you're developing, selecting the right material is critical for ensuring performance, manufacturability, and long-term reliability. When you are building devices that test blood, identify pathogens, and isolate DNA samples, there isn't much room for error. In this video, we'll explore the key factors that influence microfluidic material selection and break down the most common and emerging materials used today. The materials you choose for a microfluidic device depend first on the device's intended function and secondly on the function of that specific layer. Typically, a microfluidic device will have a desired result. For example, deliver a sample from point A to point B. In addition, microfluidic devices are often performing multiple complex functions within a small area. For instance, if the device will be used in a clinical diagnostic setting, the material must support that functionality without compromising accuracy or safety. Other key considerations include the material's durability and overall cost. Beyond that, the environment in which you manufacture, such as a clean room for diagnostic applications, can also influence your choice. Every device design has unique demands, and aligning those with material properties ensures both performance and manufacturability. Several materials are commonly used in microfluidics, each offering specific advantages depending on the application and manufacturing needs. Silicone and glass were the original materials used for microfluidic devices. Silicone offers high resistance to organic solvents and stable electroosmotic mobility, but is hard and costly to fabricate due to its rigidity and the use of hazardous chemicals. Glass, though optically transparent and electrically insulating, also has high fabrication costs and is difficult to work with due to its brittleness. Despite these challenges, glass still finds relevance in specialized applications, like on-chip reactions and droplet-based testing. Next, polymers have become the most widely used materials in modern microfluidic fabrication because they are accessible, affordable, and highly versatile. Within polymers, PDMS, an elastomer, is especially favored for its flexibility, optical transparency, and compatibility with biological samples. PDMS naturally repels aqueous solutions, making it ideal for experiments involving fluid flow and cell culture. Another polymer options are thermosets like TPE, which offers strong, solvent-resistant, and optically clear structures for microfluidics. But their higher cost and need for surface modification limit their applications. Thermoplastics are another common material that falls into polymer family. They are popular in microfabrication due to their optical clarity, stiffness, and ability to be remodeled, making them ideal for high-volume, low-cost production. Variants like BOPP and PET offer strong, clear, and easily processable options, though surface modifications may be needed to enhance bonding and performance. The third material type is paper-based chips, a newer material in the microfluidic world, popular for its low cost, global availability, and disposability. Its porous nature allows for passive fluid flow through capillary action, making it an excellent choice for simple diagnostic tests and colorimetric detection. The white background of paper also enhances visibility for color-based readouts, which can be crucial for point-of-care devices. Lastly, we have hydrogels, which are gaining traction in biological and tissue engineering applications due to their structural similarity to natural cellular environments. These highly porous materials can be modeled with microchannels to deliver cells, nutrients, or reagents, making them ideal for studying cell cultures. Because they're non-toxic and support diffusion of small molecules, hydrogels are well suited for applications requiring close interaction with living tissues. While their strength is lower than other polymers, their biocompatibility and tunable pore sizes make them valuable in regenerative medicine and biomimetic microfluidic research. Once you have selected potential materials, the next step is to evaluate the manufacturability of your design. That includes not just material performance, but how easily it can be fabricated and assembled into a final device. Partnering with a converter that specializes in medical grade and microfluidic parts is essential. It's not just about having the right materials, it's also about having the right support and expertise to take a design from a sketch to a scalable product. Getting samples, testing compatibility, and understanding the nuances of converting microfluidic components can all help prevent production issues down the road. If you want to learn more about working with the converter and how they can help bring your part to life, feel free to visit our learning center for countless videos and articles. Or you can always reach out to us directly. Thanks for watching.